Ladies and gentlemen, my name is Horst Pflügel and I would like to present a research project Obelics, which is about optimization of scalable real-time models and functional testing of eDrive concepts. The vision of Obelics is the creation of a comprehensive framework for the design, development and testing of advanced e-powertrains by usage of model-based testing methods and scalable and easy to parameterize real-time models. This shall lead to a reduction of development efforts by 40%, improved efficiency of drivetrains by 20%, and an increased safety by a factor of 10. The project started in October 2017 and lasted until November 2020. With a budget of 9 million euro, we had 19 partners from 9 different countries, which were car manufacturers, software, hardware, and tier 1 suppliers, SMEs and research organizations, as you can read here. The approach of Obelix is a front-loading approach, where critical tasks are done early in the development phases, supported by models, scalable models along the entire development process, and with testing methods which are mainly model-based testing methods. With that approach, we want to reduce the development effort by 40%. Now in Work Package 1 we have defined our use cases, and in Work Package 5 our safety assessment methods, which have set the boundaries and the requirements for the work in the project. In Work Package 2, 3 and 4 we have developed our models with real-time capability and the model integration methods as well as the functional testing methods. On the other hand side, we have formed 4 different use case clusters which represent engineering categories. The first category is eDrive concept and component sizing in early design phases with 3 use cases. In use case cluster 2 we have e-vehicle system integration and optimization based on real-world data with 5 use cases. In the category 3 we have battery design and testing for improved safety and reliability with 4 use cases. And in use case cluster 4 we have e-motor control and inverter design and testing. Now you see here 3 examples in Work Package 2, an electrochemical battery model based on macroscopic level, which is very good for representation of aging effects of the cell. Then we had an e-machine model with high fidelity multiphysics, which was where we had a generator tool that created with just 3 input parameters the complete machine. As a third example, the inverter models, which were accurate switch and loss models, where we could study the design of passive filter components at an AC/DC level. And we could do the comparison of 10 kHz with 2 kHz switching frequencies. In Work Package 3 we did system integration and optimization, where we started from a very high accuracy physical model and put in some thermal system integration models, where we could then study control strategies and automatic calibrations with real driving conditions. For real-time capabilities, there were complexity reduction of the models needed. And with that, we can do EV optimization and trade-off analysis. Finally, there was a simulation toolchain with FMI and FMU model integration, co-simulation and signal delay compensation available. In Work Package 4, we investigated functional testing methods. For the battery testing, we have realistic high-frequency testing up to 20 kHz, which was controlled by an FPGA-based controller platform. As an example, we have also developed EIS testing signals, multi-sign, for fast scanning of the battery cell. On the inverter testing side, we had a real inverter connected with a distributed hardware platform, where the models of the e-motor and the battery and the control unit run in real time. This allows us front loading in early stages of the development phases. You can also emulate sensor values, and you can eliminate bugs very early in the hill environment. On the right hand side you see a comparison between the calculation times of a PC based embedded CPU and FPGA-based calculation of the controller. Now in Work Package 5 we have created a completely new safety assessment method with a probabilistic FMEA that assigns failure probabilities. And with that we have done battery safety testing combining electrical and mechanical tests. The electrical tests have been done with silicon carbide test devices and FPGA controllers, and the mechanical tests you can see a comparison between the measured spectrum and the ISO suggested spectrum below in the graphic. In Work Package 6 we have demonstrated and evaluated our use cases, and we want to measure the impact factors. The question was how to quantify. Therefore, we have looked at the three categories, which are mainly our objectives, and looked what are the influencing factors. For the efficiency improvement, for instance, the vehicle architecture plays a big role, or the control strategy, or the thermal management. For the safety improvement, there are other influence factors like the improved battery failure prognosis, or to consider the real high frequency effects in a battery testing environment, or to reduce the vibration for the mechanical test. Then finally, for the development effort reduction, we have a lot of factors like the scalability or the interoperability of models, the hybrid testing solutions, or front-loading approaches for testing. You see there are a lot of influence factors for these final numbers. Now you can see here an example for the demonstration and the evaluation of a use case as an example 4.3, which is the inverter design and testing. This has been done at the Bower Hill setup from AVL, where the battery and the E-motor was emulated and the inverter was here in real. This allows then a 4-quadrant operation of the engine in real time, and also error stimulation and manipulation of this E-machine. There's of course no mechanical danger from the rotating parts if you have it in virtual form. The battery has been replaced by a battery emulator, and there have been performed back-to-back tests in several stages of the development. The overall effort reduction with this automatic test is 55%. And this comes together with the numbers below in this table, which you cannot see complete. But there are a number of test cases, the manual execution and the automated execution. There's a specific time reduction for each test, and if you combine that, then you see that this is 55%. If we now put together all results from every use case, then we can see that the overall reduction for the development effort is in average 56%, which is more than we have planned actually. For the efficiency improvement, we have reached a value of 16%. This is less than expected because we could not do all planned assessments for use case cluster 1 due to the Corona lockdown. For the safety increase by a factor of 10, we have done all tests in the battery cluster, and we have reached finally a factor of 15. Finally, we have done a lot of dissemination activities in different conferences, as you can read here. And we've done 30 publications, partly peer-reviewed, book chapters and proceedings. And we have been present at AirTrack EUCA, EGVIA and Klepper conferences. One highlight was the joint network event between DemoBase, Hi-Fi Elements and Obelics here in Graz, with about 140 virtual participants. As you can see here, some pictures on the right hand side. Another activity was the harmonization of the model interfaces between Obelix and Hi-Fi Elements. We exchanged our modeling approaches and interfaces, as well as these identity cards for the systems, and have found a very good suggestion for standardization. At the end of my presentation, I would like to show you our contact details from myself as a coordinator for the project management support by Uni Research and of our webpage on the internet, which contains a lot of useful information. Thank you very much for listening. I'm looking forward to your questions.